Hello and welcome along. If you're on the live stream or if you're on the replay, that's great. Good to see you. So this is my second live stream. This time we're doing electromagnetic properties of electromagnetism and the second part of the quantum course. So in this live stream today we're going to look at how you excite a gas so that it gives off photons effectively. So emission spectra. We may get on to absorption spectra as well, but we'll see how the time plays out. So kicking straight off then, this part of the course normally starts off with a demonstration of these things. So what we have here is a glass tube, as you can see, and inside this is a partial vacuum, and there might be a gas. For example, in this case we're talking about helium. Sometimes though it's not just a gas, it could be something weird like a vapor of mercury, whatever that means. Basically mercury particles flying around inside a partial vacuum, and then we put a relatively high voltage across those plates like that, turn the switch on, and if you're lucky, which you should be, you see something like this. So in other words, what we're getting here is a light is given off. So by setting it up with this way, with the high voltage and the gas in the tube, we get an emission spectrum. And what you can see is that the tube is kind of thin in the middle there, and the light is quite bright. Now these are really beautiful. I love these things. One of the best parts of the syllabus for me at the moment. If you have these, they are around about 10 centimeters long. You normally do it in the dark so you can see the light, and all the different, you get different colors from different gases. So that means you're able to identify what gas you've got in the tube by looking at its color. So let's think about that for a moment. So here is an example of what you might see if you take the light out of the center, say, of this tube and shove it through a prism or a diffraction grating or something like that. What you're going to see is part of the visible spectra. And there's quite a few things to note here. So as the light comes through the prism, it splits into this spectrum. You can see we've got a strong red line and a strong yellow line, a few blues, and then a kind of purple off the end there. And if you add that lot together, your eye will see it as this colour here. However, the prism has split it back into its colours. And a couple of things to point out is these lines are described as being discrete. So this means that what we have here is the lines are separate. There are gaps between the lines. So if you were to imagine the full electromagnetic spectrum going red, yellow, orange, you don't have any missing lines, but there's lots of gaps in this. So these lines are described as being discrete. Notice as well, although we never really deal with this, that some of them are kind of like the yellow one is wider, fatter, and you could say brighter maybe than the blue ones there. Okay, so that's what's going on. As I said, every different gas, I think every different gas anyway, will give you a different set of lines. And don't forget, of course, that just because we've said visible here, it doesn't mean that you're not going to get off things like, you know, infrared down this end and ultraviolet down that end. These spectrums often go into the invisible part of the spectrum, which is, after all, most of the spectrum. Okay, so far so good. So here's a typical question then on this stuff, which is from 22. And what we have here, I won't bother reading it, but basically we have the emission spectrum for sodium and the emission spectrum for hydrogen. Now these have been well known for a long time, so you know you're sure about these. You can literally go and look them up. But around about 100 years ago or so, when scientists first started doing all this, nobody knew about helium. Hadn't been discovered on the surface of the earth at all, and that's because it's so flipping boring, because it's so unreactive. So anyway, we get what they did was take a spectrum from the sun, and they noticed this strange set of lines, this one here, that doesn't seem to fit with anything that they knew. And the question is asking is, could this new one at the top, which of course turns out to be helium, and which they've labelled the lines, could it be sodium or hydrogen or some combination of them? So what you have to do is look along the lines and see how they compare. So let's take line A here in our unknown spectrum. You can see, I think, pretty clearly that that lines up with this line. So that suggests perhaps our new substance has got something to do to hydrogen. But then you can see that the hydrogen spectrum's also got lines like this one, which doesn't appear to line up at all in our new one. There is no line there. So that suggests that in actual fact this helium along the top isn't from the hydrogen spectrum. And then thinking about the sodium lines, I guess you could probably see, there that this line in the sodium is pretty clearly the same as line E. And yet again, we've got lines like that one, which isn't reflected in our mystery spectrum. In other words, the spectrum here is not a combination of these two. It just isn't, because there are lines missing. And this led to the discovery of a new chemical element. Now what we're really saying here is that these pretty spectra, which as I said before, I think are rather beautiful, actually are like a unique fingerprint. And so from these spectra you can do things like work out if you've got, shall we say, hydrogen gas, or if you've got, actually hydrogen's a bad example, let's stick with helium. If you've got helium gas, or maybe helium minus gas. In other words, if you've got an ion like this, or have you got an ion maybe like that, or have you even just got the straight atom? Each of those will give a slightly different spectrum. It's very cool, this, because you can identify all sorts of unknown things. Right, let's get into some more deep physics now. So this is the idea next, in order to try and explain these lines. That's what we're going to look at for the next 20 minutes or so. So yeah, don't forget, if anyone watching wants to shove in questions, that would be really great. So please, do that. Shove in a question into the chat, and I could be really excited trying to get to work out how to answer it. But anyway, there we go. That's the aim. So coming back to this then, it turns out that in atoms, you're really used to this idea of, I don't know, a positive nucleus like this, and then some kind of shell around it with an electron. And so look, there's hydrogen. We know about hydrogen, don't we? We just know it's H11, ComSat, or like that. So then what we will go on to say, or what we can go on to sort of talk about, is the fact that this electron, there's one electron in our hydrogen atom, can move out to a different orbit. Okay, so it can move out so that the distance is slightly greater. Now, this is where we're going to start waving our hands at physics, because it's not as if the electrons actually move out to higher orbits. It's not like a little solar system with the sun being the nucleus and electrons being planets. It's not like that, but it's a model. It helps us to think about it. And it actually turns out that there's a whole pile of these different imaginary levels that don't exist that we can pop our electron into. And these are often represented, because these diagrams are extremely hard to draw, so these are generally represented as being levels like 1, 2, 3, 4. And you'll notice that as we go up, those lines are drawn closer together. We'll talk about that in a moment. And they're actually up to an infinite number of levels. Now, going back to this model that's wrong, which helps us to understand what's going on, if you imagine moving out to an infinite level, so look, there's level 3, blah, 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 go out to, say that's the infinite level out there. What we've done is, if we push our electron out to that infinite level, what we're saying is the electron is now free. In other words, what we've done is we've ionized the atom. So this is like the ionization level. It's where you take the electron right up out away from the atom. Right, so that's what's going on there. Now, fairly easily actually, and you'll have to do this in some questions most likely, we can actually give levels to these lines, the n equals 1, 2 and 3. We can consider them as energy. So let's think about that a little bit. So here's the classic kind of diagram that you'll see in a book. So here's your levels, 1, 2 and so on, 3, and on the left hand side we've given them energy levels, and there's a lot to think about here. And if you look at this and think, oh yes, I really understand that, that probably means you don't. First of all, these flipping things are negative. Why on earth would they be negative? What is negative energy? Well, if you want a real explanation of that, you're going to have to wait till you do some work on the fields topic, which is probably coming up quite soon, and a wonderfully difficult part of the course in my opinion. Anyway, so what we're saying here, the best way I think to think about this is to imagine a ladder. So if you're trying to climb up a ladder, now I'm not going to try and draw a person, as anyone who knows me knows that my drawing skills are not fabulous, but these rungs on the ladder are equally spaced, and then what you have here is a mass, say, sitting on the ladder there, and then you can move this mass up to the next level. Now, because obviously the mass is acted on by gravity, because this is a ladder, in order to get your mass from level 1 to level 2, you've got to do work on it against its weight, its mg. So that means that when the mass is at level 2, it has more energy, potential energy, than it has when it's at level 1. And if you come over back to our lines, you can see that it's gone from minus 2.2 times 10 to the 18 to a higher energy, 5.4 times 10 to the minus 19. Still very small, but nevertheless, there's less energy. So it's like walking up a ladder. Now, the ladder analogy here is actually pretty helpful, because what it tells you is, coming back to our ladder, is that, I don't know about you, but I can't put a weight, or a mass I should say, sitting in the middle between two steps. I mean, maybe you can, but I've never managed to do that. And I can't sit it kind of 3/4 of the way up between steps either. I can only put the weight on a step. And it's the same with electrons, as we'll see. When electrons move between levels, they can only live on the level. So I could take that electron up from the bottom state up to the middle, up to the next state, but I can't make it sit kind of halfway or 2/3 of the way up. It's just not possible. Why, you might ask? Well, that's a very good question. It actually used to be on the syllabus, but isn't anymore, so I'm going to park it for the moment. Maybe that's something we could think about later, perhaps. Right, moving on then. So these numbers, just live with the fact that they're negative for now. Notice that the infinite level is defined as being 0. Again, that's weird. And notice that these numbers are getting bigger as you go up. Right, so now these numbers are fine in joules. Remember, energy is always measured in joules, but they're difficult to work with. So what happens next is that these levels, you know, these nasty numbers like 2.2 times 10 to the minus 18 are converted into electron volts. It's at this point really that you perhaps first realise just how flipping useful electron volts are. As I said, I need to do a live stream on electron volts. It's notoriously badly understood. Anyway, leaving that to one side for a moment. So you can see that the lowest level is minus 13.6 electron volts. That means if I want to take Johnny Electron, don't know why I call it Johnny, just always have, that's sitting on that bottom level there, and I want to excite it so much that it escapes completely, I have to give it 13.6 electron volts of energy. Now, if any of you are doing chemistry, and why would you be, what you're going to realise at this point is that 13.6 EV is what they call the ionization energy for hydrogen. In other words, it's the energy to knock off the only electron that hydrogen has. And you can see it represented here. That's what we're doing. We're taking it from n equals 1, also known as the ground state, all the way up to the infinite level, where it's got no energy. Right then. So more and you can see these electron levels, as you'd expect, getting closer together. There's less distance between these two than there is compared to these two, unlike the ladder, which is equally spaced. Right, now let's get into the nitty gritty. So what we've got here is just two of the levels, the bottom two levels, and I'm going to talk about what happens when we excite or de-excite the gas, the hydrogen or the helium, whatever it is. It's hydrogen for us, isn't it? So what we're going to think of, we've got our little electron here, and we're going to excite it somehow. I'll talk about exactly what that means in a moment, but just think about the word excite. If you have a small child and you tell them that you've got a surprise for them, they're going to start jumping around going, ooh, 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 give me the surprise. They're excited. They've got more energy. It's just the same with electrons. So if you tell this electron that you've got a present for it, if it gets the right amount of excitement, it will jump up to this next level. It will then leave n equals 1 or ground state and go and live in n equals 2 for a bit. Now the thing is how much energy is needed to do that, and it's time for me to bang on one of the drums that I like to bang on. Any change in physics, any delta, is always equal to the final value minus the initial value. So final value for our electron's energy is 3.4, only it isn't, it's minus 3.4. electron volts. And then we're going to take away the initial value, which was minus 13.6. So minus 13.6 electron volts. And when you do that, obviously, they become a plus, and you end up with 10.2 electron volts. Right, now this is a big deal. What this means is that it's going to take 10.2 electron volts to get Johnny Electron from level 1 to level 2. If you try and give it 10.1 electron volt, it's not going to happen. It's not going to go up like to here and just stop. It doesn't happen. It just stays fixed. Okay, it just stays fixed. So it has to be exactly 10.2. Right. Now, a moment later, now how long is that moment? Well, that's a good question. It's not very long, to be honest. So nothing in nature likes to have more energy. You know, think about you. You like to just slouch about, don't you? So do I. We all like to rest. But an electron, when it's excited, will wants to de-excite. In other words, what it has to do is it has to lose that energy. And that energy is going to be, guess what? 10.2 electron volts. It has to be the same thing here. Now here, in a way, is the key point. How does an electron lose energy? Well, in this, I mean, there's lots of ways. That's a bit of a vague question, isn't it? But this electron, on its energy levels, is going to lose energy by emitting it as a photon. So there comes a photon, often given the symbol gamma. So it's going to emit a photon which has to have that much energy, 10.2 electron volts. So that means that we remember the formula for photons from the last session. The energy of a photon is Planck's constant times the frequency. Now this is fixed, isn't it, Planck's constant? So that means if we do 10.2 eV divided by Planck's constant, we are going to get the frequency of this photon that comes off. Now, as you can see, this frequency value is one value. It's fixed because any electron that falls from 2 down to 1 is going to lose 10.2 electron volts. Not 10.3, not 10.1, but 10.2. Therefore, they'll all have the same frequency. Therefore, they're all going to look the same colour. Alright, let's take that a little bit further. This time, what happens if we've got two levels? Okay, now this is a little more, you have to think a little bit more about this. So we worked out that going from that level to that level was 10.2 eV. So we could do the same thing, final minus initial. And let's think about what happens this time if our electron travels from level 2 and is excited even more up to level 3. Well, we know change is final minus initial, and the final is minus 1.5. Take away the initial, 3.4, and that leaves us with 1.9 eV positive. That means to go from level 2 to level 3 is going to be 1.9 eV. So what do you think it would be if we took an electron and we jumped it up from 1 to 3? Yes, well, it's going to need 10.2 plus 1.9, which is a number that I can't actually remember off the top of my head. So I'm just going to check my notes. Yep, 12.1. So that is actually 12.1 electron volts. Now, the thing is, you have achieved the same thing. You've lifted the blue electron from 1 up to 3, and you've lifted a red one from 1 to 3. But they've done two different routes to get there. So that means we're getting different bits of energy. In both cases it's 12.1, but in one case it's made up of two little packets of energy, 10.2 and 1.9. Righty-ho. So a bit later this could do the opposite. So let's work it back the other way now. Let's suppose we've got an electron that is sitting. I'm just going to put that 2.9 back. Actually 1.9, isn't it? Just put that 1.9 back there, just so we've got it. So we've got an electron sitting on level 3. It, as you probably know, could fall back all the way down to the bottom. Now if that happens, let's call that transition 1. Transition 1 is going to give off an energy of these two added together, 12.9 eV. So in other words, we're going to get a photon that has that much energy. But perhaps our electron, when it's at level 3, is going to drop back to level 2 and then drop down to level 1, in which case we're going to get 2 transitions. So in this case, transition 2 is going to have an energy equal to 1.9 eV, and transition 3 is going to have an energy equal to 10.2. So in other words, what we're getting now, by introducing another level into our setup, we've now got a situation where we are getting 3 distinct frequency photons coming off. In other words, we've got 3 stripes of colour. And I think you can see, let's just ask the question then. So looking at this, 1, 2 or 3, which do you think is going to have the frequency of light that is closest to red? Closest to red. Well, thinking about the spectrum, you know, you've got red at one end and blue at the other. The red has the longest wavelength, the lowest frequency, so it has the least energy. So the red will be the lowest energy. So number 2 is likely to be a red colour. Number 3 is slightly more energy, so that might be sort of a orangey colour. There we go, I actually got orange. O-R-A-N-G-E. And number 1, because it's even more, will give us maybe something in the yellow bit of the spectrum. So you see, we're getting 3 distinct lines. Okay, and I can see I've got the most, so 3, I mean 1, I mean 2. Okay, right, I hope you get it now. Who's ever writing the answers to that question in there, it's nice to see we've only got a really short delay, like about a few seconds. Mr. DJ sir, nice to see you there. Hopefully that's kind of cleared that up for you. I can see there's another question in there about the extra energy, but I'm going to come back to that one. That will become clear, I think, when we talk about how it is that these electrons can get bopped up and down these levels. Okay, so I'm going to move on now. Let's put this into the context of a question. It's always good to do that, isn't it? So this one here is a very common style of question across all the boards. You're very likely to get something like this, whatever board you do. So we have 3 energy levels. Now, first of all, notice something different here. They've been sneaky, right? They have talked about a ground state, level 1 and level 2, whereas we have been talking about n equals 1, n equals 2 and n equals 3. So they've changed their nomenclature to give it its posh word, or to give it a not posh word. They've labelled it different. Yeah, but don't be put off by that, yeah? That's no biggie. We can still work with that. We know what the ground state means. And we've been given some transitions of electrons are happening between these levels. So why don't we think about what transitions we could get here? Well, what is the difference between the energies of the ground? I'm just going to step back right here. Here we are talking about the production of photons. So that means if we want to think, oh, we're having electrons doing this, or are we having electrons doing that? Are they going up or are they going down? Well, clearly they're going down, because as they go down, the energy is released. Energy has to go in to get them to go up. So we're talking about dropping levels. So what drops can we have in this setup? Well, obviously we can have 2 to 1, we can have 2 to the ground, or we can have 1 to ground. So we've got 3 possible transitions. So let's well, there they are, 3 possible transitions. Now, which of those transitions is going to give you the biggest energy? Biggest energy. Is it number 1, number 2, or number 3? Which is the biggest energy? Well, you know, given that we've got a delay, it's the one that does the biggest drop. Hopefully you got that right this time. So number 2 is going to be the biggest drop. If it's the biggest drop, it's the most energy. And because we know that E equals HF, if we've got the most energy, we have to have the biggest frequency. So looking carefully through the list, we can see that this one at the bottom has the biggest frequency. Be real careful here, because these numbers look very similar. And I've had students doing this question who haven't noticed that one of those is 10 to the 14s and the other is like 10 to the 15. So don't get fooled out by stuff like that. Yeah, right. So number 2 is the biggest energy drop. So that is going to be 2.92 times 10 to the 15. So that's number 2. Alright, and so what's number one? Well, number one is the smallest energy drop, isn't it? So this time it's going to be, if it's the smallest energy drop, it's going to be the lowest frequency. We're looking carefully at the numbers, we can see that that one there is the lowest frequency. So that means that the middle one there must be going from, or must be number 3, because number 3 is the middle length of wire, the middle arrow length, which means it's the middle energy, which means it's the middle frequency. So it's got to be 2.4 times 2.46 times 10 to the 15 hertz. All right. Now the question says to you, what is the energy difference between the ground state and energy level 1? Well, that corresponds, as we've just seen, I hope, to this transition, because it's level 1 to the ground state. So we know that our delta E is going to be equal to H Let's see if we've got interweb. Looks like we have. Yeah, well, you know, it's going to happen, isn't it? Okay. I think we're back. Looks like we are. Yeah, we are. Well, I don't know if anyone's still there, but I'm still here. Okay, sorry about that. Technology, eh? I wonder if I can cut that out of the real thing. Well, yeah, weird, isn't it? Thanks for telling me it's uncut, it's unfrozen. So I'm getting a message today it's back. So look, we were just talking about how is it that electrons can get up from one level to the next. What is it that makes them do that? Well, there are basically 2 ways that this happens that you need to know about, and this, I find students get confused about this, and the reason often is because of this bit, particle collision. So we'll spend a moment here. So here we have a hydrogen atom which has 1 electron sitting there like that, n equals 1, just doing its thing. And we've talked many times now that to get that electron from that first level to the second level, that we need 10.2 eV, like that. Now, one way we can make this happen is by getting another particle, so let's just leave it blank for the moment, and firing it in. Now, if this particle was if this particle is something like a helium particle, or even a helium-2+, which of course you know as an alpha particle from GCSE. Remember these little alpha particles? They're very ionizing, and they're also very heavy. So if this was a helium nucleus, or alpha particle, comes flying in, hits this first electron, and just completely blows it out of the atom. It gives it more than the 13.6 eV needed to ionize it. Now let's say this comes in, I'm just making up silly numbers here, but let's say this comes in with 15 eV. That's its kinetic energy. It hits our electron, young Johnny over here, who is sitting at minus 13.6. Remember, that's the energy needed to take this electron right out to infinity. Well, it's been given 15. So in this case, what happens is that this electron comes off, not only gets out to 15, it's become ionized, but this alpha particle will come in, do its collision, bounce off, and instead of having 15 eV, it will now have 15 eV minus 13.6. In other words, 1.4 eV. So it's got less kinetic energy left over. So that's what happens to the extra energy that goes in. If it's a particle like this, the particle just bounces off. So let's bring it back into the real world a bit now. I mean, that was the real world, but it's not kind of the real world that you really need to know about so much at A level. So what you're more likely to come up against is electrons coming in, and this is where the confusion is, because we have an electron here that is bound, sitting in a hydrogen atom, and we have a free electron here which is whizzing around. And when you write your explanations for this question, the big problem that people have is they get confused, because we've got free electrons and we've got bound electrons. Now, bound means joined together, literally stuck together in the atom. It's connected due to the positive and negative charges. I mean, it's not joined, but it's attracted strongly. It's bound. The bound one is also known as an atomic electron, although that's a bit more old-fashioned. You don't see that so much. Mostly our syllabuses talk about bound electron. Right then. So we know that we want to provide 10.2 eV to get Johnny electron there from level 1 to level 2. Let's say that this again has 15 eV. Well, I think you know what's going to happen. This comes colliding in. I'm going to say somehow the bound electron knows that it needs to take 10.2 to get itself up to that first level. So it's going to take 10.2, meaning that it's excited into this level, meaning that our electron can bounce off with the difference of 15 minus 10.2, whatever that is, 4.8. So in other words, our incoming free electron now has 4.8 volts, electron volts of kinetic energy. Now there's all sorts of little complications here, because it could be that this bound electron has enough energy to go up to the next level, which is a possibility. So coming back to this chart, we can see that the total energy to go from the ground up to the top was 10.2 plus 1.9. So if I've given it 15 eV here, it could be that our friend Johnny electron goes from 1 to 2, or it could be that it goes from 1 to 3, in which case this one will bounce off with a bit less energy. Alright, so we can do collisions to cause these things, these electrons, to get excited. Now guess what? Right back at the start, we had this little circuit. What's happening here is that we talked about hydrogen, didn't we? But this all works with helium, pretty obviously. So in here, we have a whole pile of helium atoms with their little, in this case, 2 electrons, and the possibility of levels, just like we've been dealing with. So there's one level. This is very hard to draw, so I'm not going to draw the whole circles, but here we've got n equals 1, n equals 2, n equals 3, and so on. Right, so we have this gas of helium. Then what you do is you put a big voltage between these plates. So the potential difference between those plates is 1000 volts. Now what that means is that if you just happen to have, notice what I said there, a free electron in there somewhere, that's going to feel a great big attractive force towards this positive plate here. So this is going to accelerate, and very soon it will have enough kinetic energy to excite one of our helium atoms. And if that happens, that helium atom will become excited, the electron goes up and it falls back down a bit later on, and off comes a photon. So as long as you've got some electrons hanging around inside this tube, then you can accelerate those electrons because of the attractive force and cause them to excite the helium atoms and therefore glowing. Now you might say, well, what if I haven't got any electrons hanging around in that tube? Well, then you've got a problem. But the thing is, if you have any gas, what you will find, well, any gas or any bit of stuff really, you will find is that you have free electrons hanging around. There just are free electrons hanging around. After all, for example, you know about background radioactivity, which gives off perhaps alphas or betas and ionizes things. Free electrons. So there will be some free electrons inside this tube, whatever. And the other thing is, of course, if this voltage is high enough, it could pull off electrons off of the surface of the cathode there, and they become free electrons. So there's 2 places really that these electrons can come from. But yeah, so there's 2 places. They're free in the gas anyway, That's actually a third place. They're in the gas anyway. They get ripped off the cathode, and if they accelerate fast enough, now this is 1000 volts, they're going to be accelerated pretty quick. They're going to get a lot of kinetic energy. They will then go on and ionize some of the helium atoms. And if they ionize some of the helium atoms, you're going to have a pile more electrons. So you might start off with literally just one baby electron all on its own in the tube there. Because it accelerates so fast, it ionizes a helium. Bingo, you've got 2 electrons. And then they go off and ionize some more heliums. Bingo, 4 electrons. And so it grows and grows. So that's one method for how we can create an excited gas, and then from that get these beautiful spectrums. Okay, now it doesn't have to be an electron that goes whizzing in here, it just is in these tubes. You could also imagine a situation where you heat a gas enough that the particles within the gas collide so much that they ionize each other. Off you go again. Well, let's go back to the other system. Right, remember we said there are 2 routes to excitement. 2 routes to raise these electrons up to higher levels. Well, one of those is with particles or collisions. The next one that you need to know about is the photon version of this. This is slightly different. Now you remember there's a big old thing in this topic about 1-to-1 interactions, you know, if you remember that. All right, so one photon collides with one, well, it was electron when this is introduced, it still is, isn't it? So one photon collides with one electron to create one electron. Okay, I didn't really like that. I had that clear in my head, but it kind of left me. What we're saying here is with photons, when photons interact, they do a thing called a 1-to-1 interaction. Now what that means is that they give all their energy away in one hit, or they give none of it away. So remember, in comes an electron, it collides with, say, I don't know, an electron inside. In comes a photon, collides with a delocalized electron. If it has the right energy, it can give all its energy up, or else it just passes on and is not absorbed at all. It's all or nothing. So in comes a photon. We have our Johnny electron sitting here. We know that he needs, or it needs, 10.2 eV to get it to the next level. Let's say that this photon has 8 electron volts. Well, 8 is not the same as 10.2. Clearly, it's less, isn't it? So this photon is going to come along, it's going to wave hello and zoom on by. In other words, nothing's going to happen. Nothing. If we give this electron 18 eV, now we've got an issue. Because it could be, remember we said right back at the start that these things have lots and lots of levels. Remember, lots and lots of levels. It could be that, say, going from level 1, I don't know, I'm just making numbers up here, to level 7, just happens to be exactly 18 electron volts, say. If that's the case, then this 18 electron volt photon, when it comes in, will zoom this all the way up to n equals 7, and bingo, it stays there. But the photon will be totally absorbed. Now, more likely, because 18 is unlikely to happen really, especially when you think 13.6 is the ionization energy. Suppose we come in then with a photon this time of 10.4 eV. Well, the thing about 10.4 is it is not 10.2. So again, the 10.4 will wave a cheery hello and just go past the electron. However, if this photon that comes in is 10.2 exactly on the SNOS, then now, this is the clever bit, our little electron friend, it knows that the photon is 10.2. In other words, it can absorb that photon fully. So the photon comes in and gives up all its energy to our bound electron, which then gets excited up to level 1. And the photon ceases to exist. So the main difference really is that if the photon doesn't have the right energy for a jump, nothing happens. If the photon has exactly the right energy for a jump, it's absorbed and ceases to exist. With a particle, if it has less energy than the jump, nothing happens. But if it has more energy than the jump, you can get a jump, and the electron will lose the energy equivalent of that jump. In other words, it's going to slow down. So it's a different kind of interaction. So try, when you get these questions, because you will do, when you get a question like this, try to be clear. Is it a photon that's doing the excitation? Or is it a particle that's doing the excitation? Because that's the key point, really. Right, we are getting towards the end now. No doubt you'll be delighted to think. So, one last question. So this one is taken from, I can't remember. I think this is an edit set. No, it's AQA. I'll tell because of the boxes. So here we have a little question that's 3 marks and it wants you to write something. So I'm not going to go over a long answer here particularly. We'll just give you some pointers. You may well be able to see where you need to go. So line emission spectrum of hydrogen and anti-hydrogen have been compared. So hydrogen, of course, you know, is a plus proton and an electron whizzing round. But anti-hydrogen, well, that would have an anti-proton in the middle, which of course is negative, and a positron going around the outside. Now these 2 particles, the positron and the electron, will have the same mass, and the proton and anti-proton will also have the same mass. So the question in my mind is, do these 2 have the same spectra? Interesting. Don't know the answer off the top of my head. Because of the similarities, I rather suspect they do. Thankfully, though, we're not asked about that. What we're asked about is, in terms of energy changes, how the line emission spectrum are produced. Right, so really this is pretty, well, I want to say straightforward. Of course, it's straightforward if you know the answer, isn't it? So the first point that they want you to talk about is that the electrons exist in levels. Now, we've been talking about that, for the last half an hour. So if you haven't got that yet, you've got a problem, okay? So electrons exist in levels. So that's the first thing. Now, it's talking about how emission spectra. So are we exciting or de-exciting? Well, we're de-exciting. We're going down. So your next point is going to have to say something about electrons de-exciting. Now, you don't have to use the word de-excited. You could just say drop to lower levels. But as that happens, you might want to say something along the lines of emitting a photon. Alright, so existing levels, de-exciting and emitting a photon, and then that photon, gamma, remember, is a symbol for a photon, has the energy HF. And since the levels are discrete, i.e. very separate, since levels are discrete, that means discrete. That means itself that the frequencies are going to be discrete. In other words, you're going to get lines rather than a block of colour. So since levels are discrete, this implies that the frequencies are 2. So that's what we're looking at. Existing levels, they drop down emitting photons, and because these levels, in fact, you know what, to be really to make this even easier to answer, if we'd put the word discrete in there, descrete, then we wouldn't have had to say this bit, which would perhaps make it easier to write out. Electrons exist in discrete levels. Electrons de-excite, given off photons, and E equals HF means that the frequencies are discrete. And really, that's it. Okay, so that's the end. I'm done. Hopefully that was useful for you. If you've got any more questions afterwards, you can always put them in the comments when this goes up sometime tomorrow. So, yeah. Bye for now. Thanks for coming.